Now, there are two groups of sedimentary rocks. The first group is called Siliciclastic rocks. And silici stands for silicate minerals. And the clastic part here stands for, well, it's Greek for broken. And so these rocks are composed of broken minerals, broken rock-forming minerals. Remember, the rock-forming minerals are the silicates. And so little feldspars, quartz, micas, hornblends, all those minerals involved in the rock in forming igneous rocks primarily. The other group is the chemical or biochemical group. And this one we separate into an inorganic group, which involves no organism, right? And the biochemical group involves basically the skeletons and shells of once living organisms. We'll talk about this group in a little while. But let's go back to this Siliciclastic group. I think your book calls it detrital. But the problem with that is a lot of these rocks over here, these chemical rocks, can also be detrital. So I like to use Siliciclastic because it really refers to these silicate minerals that are broken. Now, remember, this disintegration it involves physical weathering. So you have a bigger rock and it's broken into smaller particles, smaller and smaller. That's the idea that's going on here with this physical weathering. And for sedimentary rocks, or these Siliciclastic rocks, the way we distinguish the different the Siliciclastic rocks is we have gravel size, sand size, and mud size. So these really should have the word size, because these are size ratings that we use in geology, mud size. So gravel size is anything coarser than 2 millimeters, right? Anything coarser than 2 millimeters, whereas sand is from 2 millimeters to 1/16 of a millimeter. 2 millimeters to 1/16 of a millimeter, that's sand. And then the mud size is going to be less than 1/16. This 1/16 is basically, you can't see it without the aid of a microscope. So anything finer over here, this mud size is too fine, too small to see with a naked eye. You would need some sort of magnification to see it. And in this category, we do talk about silt and clay. Just remember that clay is finer, silt is going to be gritty. Now, if we look at the sedimentary rocks that are in the mud size category, there is something called mudstone and something called shale. Mudstone is blocky, it's more massive, whereas shale is said to be fissile. And fissile means it's layered or flat like a pancake. And so, in fact, here I have the famous Monterey Shale. And the Monterey Shale, you can see it's very thin. This is a famous formation in California that's a source of hydrocarbons, petroleum. And we'll talk more about this Monterey Formation in a moment. But here is a shale, fissile. And I want you to contrast that with a blocky, here's a block of mudstone, right? So we got some mudstone, again, very fine grain. You really can't see any particles in here. Something less than 1/16 of a millimeter. Now, in terms of sandstones, we define sandstones based on the minerals we see, whether it's quartz. So here's an example of a quartz sandstone. Let's zoom in a little bit on this guy here. And you can see grains. You see those shiny grains flickering in the light? Those are all quartz grains. You can see the sort of shimmering of the quartz grains in the light there. So this is sand size composed entirely of quartz grains. This type of sandstone is common to a passive margin like the East Coast. If you've ever been to the beaches in Florida or the Carolinas, they're quartz beaches, they're white beaches. Whereas our beaches, they're kind of beige or brown because they have other minerals mixed in. This Arcos sandstone is characterized by having feldspar, particularly potassium feldspar. So here's an Arcos. So you see these big feldspars. In fact, this guy is almost bordering into gravel size. But you can again see the sand size grains, and it's composed with a lot of feldspar. There's also quartz in here as well. In fact, it's about 50% quartz, 50% feldspar. Again, an Arcos, feldspar, and quartz. And then this last one here, this lithic sandstone. Remember, lithic means stone, so it's usually bits of other rocks in the sandstone. And wacky means it's very immature. In other words, it maybe has some mud mixed in with the sand. But you can see right away that There you do see grains in here, but there's some dark grains, some green grains, a variety of different grains in here, indicating that this is a very immature sandstone. It hasn't had a long history. We'll talk more about that when we get to sandstones and plate tectonics. Now, in terms of the gravel-sized particles, if the grains are rounded like this, then we call it a conglomerate. So here is a conglomerate. You can see usually in the environment, this must have traveled down a river some distance, and the sharp edges of the grains were weathered away, abraded away. And so a conglomerate has had a little bit more history in terms that it's traveled in a high energy environment, and the sharp edges have been worn away. Now we'll contrast this rock with the breccia, and the breccia is more immature. In fact, this would be like something you'd find at the base of those talus slopes. And so here we see a breccia, a lot of the sharp edges. See the straight edges here? Sharp edges on these clasts. Remember, clast is a broken particle. So these clasts still have sharp edges, so this would be more immature. It's higher up the valley, hasn't traveled down the river yet. Whereas once I get this moving down a river, it's going to turn into this, right? So conglomerate, rounded clasts, breccia, angular clasts. So there's a fundamental difference there. Now, let's look at, well, in fact, we'll introduce a biochemical chemical group. Now, in this group, there's basically two types. There's one that's going to be organic and one that's going to be inorganic. And the first one is the inorganic chemical group. And so, remember, in this one, there's this hydrolysis, which involves ions in solution dissolving the minerals. That material gets in seawater. In fact, seawater is primarily it's a solution, and the solution is really a mixture of something that's dissolved called a solute, and those are the salts, the ions, and water. Water is a solvent. It's doing the dissolving. And so in seawater we have sodium, chloride, calcium, this ion called bicarbonate ion, the sulfate ion, the phosphate ion, magnesium, potassium. Basically, seawater has every element on the periodic table. It just comes from rocks, right? But eventually, when seawater evaporates in a salt flat or a tidal basin, you make rocks called evaporites. And those are the salts. And so what I want you to understand is salts are not just sodium and chloride. Remember, that's halite. But salts involve magnesium sulfate, which is called Epsom salt, calcium sulfate, which is called gypsum. That's one of our minerals. Calcite, which is calcium carbonate. Sylvite is a potassium chloride. All those are examples of salts, so you can make a variety of them because you have a lot of ingredients up here in seawater to make these different evaporites. So evaporites are examples of sedimentary rocks formed by evaporating water. Death Valley, the dry lake beds, salt flats, those are forming there as well. All right, well, let's stop here and then we'll start with chemical and biochemical limestones.